everyone, so welcome back to another video. Today we're going to be doing parametric equations, and it's going to be mostly a walkthrough kind of style. I've got my notes from my lecture and I'm just going to be walking through it except an example at the end. So hopefully it's going to be an entertaining format. It's going to be a new format, so let's see how it goes. Okay, so parametric equations, what do they mean? A parametric equation means that there's just more variables than just x and y. So it just means there's many variables, and let's see how that goes. Okay, so let's say you have a graph that looks like this, right? That this is y and this is x, and it's kind of the position, the plot of a position, right? Imagine every second we plot the position of an insect. I think I copied this wrong. I think the professor was saying the path of a particle, but you can think of it as the path of an insect. Basically, we can't write this as a function of y equals something x. We can't write it. Why? Because, well, you can see how it fails the vertical line test. Or yeah, like it's a graph where it's very hard to kind of find what is its kind of, how do you plot it? How do you express it in terms of y and x? You can't. And in these cases, and in the cases where we're going to be working on examples, and the cases where we're going to actually use parametric equations in real life, there's usually another variable, and in that case, that's time. And that's why it's called parametric. So let's think about it, okay? So suppose we have x and y that are functions of another variable t. X equals ft and y equals gt. So you can see how x is a function of t and y is another function of t. They're not the same. These equations are called parametric equations because t is the parameter, right? So for example, if there was a function y equals fx, then x would be the parameter for that function. But in this case, we're referring to parametrics as it has a common parameter. You know what I mean. And as t varies, the point x, y is equal to the function of t, ft, and gt, which is a translation of just x equals ft. We put ft in place of x, and y equals gt. Okay? The plot of these points trace out a curve, which is called the parametric curve. Okay, so hopefully you can see, especially with this, how as t varies, you know, t goes from 1 second to 2 seconds to 3 seconds to 4 seconds, x and y changes. And x and y changes because x is a function of t and y is a function of t. So let's keep going. So let's say that we have a, let's start on this top here. I'm going to zoom in to make it a bit harder to see everything. X and y is a function of t. So x equals cos t and y equals sine t, and t exists between 0 and 2 pi. So let's plot it out. The first method to work with parametric equations is to plot the individual points and then see what that curve makes. We're going to move on to a second step later, but let's see how this goes. So let's ignore the plot on the right side. I'm trying to cover it with my hand, but you guys can't see that. So look at the left side only, this side, right? On this side. For every t, right, let's say t equals 0, pi over 6, pi over 4, pi over 3, pi over 2, pi, right? All these kind of t values. And then x and y each has a value of their own. So if I zoom out far enough, you can see what x and y is. So x is cos t, so cos of 0 is 1. Y is sine t, sine of 0 is 1. So you do all of that here, right? And that gives you a bunch of plots. And if we plot this out on a graph, what you get is, okay, so when x is 1, y is 0. Right? Because when t is 0, x is 1 and y is 0. So when t is 0, x is 1 and y is 0. Okay. When t is pi over 6, x is root 3 over 2 and y is 1/2. So root 3 over 2, 1/2. And then root 2 over 2 and root 2 over 2 and 1/2, root 3 over 2, and then 0 and 1. So you can see how it kind of traces out a circle, right? This is the parametric curve. And the fact that it's a circle is just indicative of, because that's the definition of cos and sine, is that they trace out the horizontal and the vertical components of a circle. But that's outside of parametric. That's not a parametric thing. But you can see how by plotting the different points, we can get a curve. And sometimes you want to get rid of t. This is the second method. We can get rid of t, right? So you can say x squared equals cos squared t, y squared equals sine squared t, x squared plus sine, y squared equals cos squared t plus sine squared t, which is equal to 1. And so now there's no t in the equation, right? T is still here. Cos squared t is still in the equation. X squared plus y squared equals cos squared t. T is still there. But when you use the trig identity to remove this and turn it to 1, there's no more t in this equation. And this is the definition of a circle, the graph of a circle. So yeah, this is what it kind of looks like. So there's another method. Actually, no. Those are the two methods, whether you plot it or you use algebra to kind of remove it. Those are the two methods to construct a parametric curve. So then let's say we had another example. Let's say we had x equals cos 2t and y equals sine 2t. Well, you can still use the same algebraic method and you'll still get x squared plus y squared equals cos squared 2t plus sine squared 2t, which is equal to 1. X squared plus y squared equals to 1. The same thing here. X squared plus y squared is equal to 1. But we are losing information. Why? Because this is cos 2t and sine 2t. If we were to do this kind of plot, right? But instead of cos t, we use cos 2t. Instead of sine t, we use sine 2t. What you'll see is that the circle repeats itself. So when there's cos 2t, it does 2 loops for the same amount of t's as the first one. The first one only does 1 loop when the second one does 2 loops. So by using the algebraic method instead of actually plotting it out and seeing how the points change over time, what we do is we lose information. We lose information about the motion of the particle. So in physics, if you were looking at experimental data, or you were modeling things, then this is something you got to worry about. With the math that we're doing in Calc 2, we don't have to worry about it, but it's just something to keep in mind. So let's use another example. So all these examples here, let's try, right? So we have x equals t cubed and y equals t. So how do we get rid of the t? Well, x is just, well, actually, in this case, I used x minus y cubed, which is 0. So x minus y cubed is t cubed minus t cubed, which is equal to 0. So therefore, x equals to y cubed. But another method you can do is if you had x equals minus t cubed and y equals minus t, well, minus t cubed is just minus t, all of that cubed. And so we can rewrite this and we can say x equals y cubed. And same thing here, x equals t to the power of 3 over 2. And we have y equals root t. So if we rewrite x as this, t root t, and then all of that cubed, well, that's simply y cubed. And finally, again, e to the minus 3t, e to the minus t, that's just e to the minus t cubed. Therefore, x equals y cubed. You can see how all of these different kind of parametric equations, even though they start differently, and they very definitely have a different kind of path, when you algebraically remove the t, you end up with the same parametric curve. So that's the kind of issue. Well, physically, mathematically, we won't have to worry about this. After this, we won't have to worry about this, but it's just something to know. And for example, like if you look at case 3, right, we lose a lot of information. And if you look at case 3, y equals, this is case 3, y equals root t. You can't have a root of a negative number, therefore t cannot be below 0. Right? And for case 4, what you have is e to the minus 3t or e to the minus t. Exponents. If t is a range of numbers that has a domain, like a complete domain of real numbers, right? E to the minus t cannot be a negative number. You can't have e to the power of something that makes the thing negative, right? E to the minus 100 is going to be negative. So therefore, y cannot be negative. So these show the different kind of complexities and the differences in kind of the way, if it was a real physical thing, the thing would be moving differently. But if it was, but mathematically, we don't have to worry about it. And in this Calc 2, we don't have to worry about it just right now. It's just something to keep in mind. But after this, we won't have to worry about this. Okay, so now let's move on to calculus on parametric curves. And we're going to take this slowly, but basically, we'll just take this slowly, but this is kind of the main focus of parametric curves in Calc 2. We don't have to worry about the physics thing. There might be a few questions about it, but generally you just want to be familiar with it and you want to be and know it exists. Okay, so how do we find the slope of a tangent line? Well, the slope of the tangent line on top of the parametric curve, right? Well, if let's give an example. X equals ft and y equals gt, and we suppose that ft and gt are differentiable, right? Therefore, dx over dt equals f dash of t, and dy over dt equals g dash of t. And this is not parametric yet. Literally, we're just saying dx over dt is just ft over dt, which is f dash t. Same thing over here. We're just differentiating for now. Therefore, now if we say if dx over dt is not equal to 0, then dy over dx, remember y over x, y and x, this is the parametric curve. Y over x, right? This is the weird thing, right? So y and x, dy over dx is equal to dy over dt over dx over dt. And if you think about it, it's almost like if you're canceling out the dt's. It's not really mathematically how it works, but in terms of the rate at which we're changing, it actually does kind of cancel out. But that's what we're basically doing. dy over dx is dy over dt over dx over dt. We're canceling out those dt's. Just think about it like that. Therefore, dy over dx, let's say that we're trying to find the tangent at, let's say, this point. The gradient of that, right, y equals mx plus c, the gradient of that, the m, is equal to g dash t over f dash t, which is just dy over dt over dx over dt. The dt's cancel, you get dy over dx. Pretty simple. And the reason why we don't want dx over dt to be equal to 0 is because we're dividing by dx over dt. You see this? And that's just going to cause an error. So we cannot do this when dx over dt is equal to 0. Okay. So this is kind of the takeaway here. So hence, the tangent line is horizontal if dy over dx is equal to 0, right? If dy over dx is equal to 0, then the curve is going straight. It's like a curve like this, and oops, a curve like this, and like we're taking the tangent all the way at the top, right? Therefore, the gradient at this point here is going to be equal to 0. dy over dx is equal to 0. And if we want the whole kind of the quotient to be equal to 0, then the numerator has to be equal to 0. Therefore, dy over dt must be equal to 0. And dx over dt can't be 0. First of all, because you don't want to be divided by 0, but also there's another nuance we'll talk about later. If we want to find a point that is vertical in a parametric curve, then dx over dt is equal to 0. And if you think about it, it's just if you had like a curve that goes like this, right? Which is not a function because it fails the vertical line test. But curve like this. This is y equals mx plus c. But then mx is infinite, right? M is equal to infinity. And to infinity, you have to be dividing by 0. So the tangent curve is going vertical if dx over dt is equal to 0, and that's because dy over dx is going into infinity because you're dividing by 0. Does that make sense? And we can't have dy over dt be equal to 0. And that's because if you have dy over dt equals 0 and dx over dt equals 0, what you end up with a 0 over 0 form. And with the things we've done with L'Hopital's rule and all those kind of things, you do not want a 0 over 0 form because then you have to do extra steps. So you cannot evaluate the gradient of it while it's 0 over 0 until we learn the alternate method, and I don't know the alternate method. So yeah, we're just going to do this example, and then that's the end of this video. So hopefully that's been a good introduction to what a parametric curve is and how all those things. So let's try this. We have x equals t squared and y equals t cubed minus 2t. I'm going to rewrite it down here. X equals t squared, y equals t cubed minus 2t. Okay, so we want to find the equation of the tangent line at t equals 2. Okay, so to find the equation of the tangent line, if we remember dy over dx, dy over dx is equal to dy over dt over dx over dt, right? And so let's try to find dx over dt and dy over dt first. So let's do dx over dt is equal to 2t, and dy over dt is equal to 3t squared minus 2. And therefore, if we say at t equals 2, because remember, what we're trying to find is the tangent line at t over 2. So we're trying to find the gradient of that tangent line right now, and we're going to find the other parameters. At t equals 2, dy over dx, because that's the kind of gradient of the function. If you think about it, the parametric curve is made up of plots, right? Each of these is like a point from the x and y, and then that makes the curve. So this is y and x, right? So we're trying to find the gradient of this. So dy over dx is equal 2, okay, so we had dy over dt, so dy over dt is 3t squared minus 2 over dx over dt, which is 2t. And then therefore, let's put 2 into t, so that's 3 times 2 squared is 4, minus 2 over 2 times 2 is 4. And so what we end up with is 12 minus 2 is 10, 10 over 4, so that's equal to 5 over 2. So therefore, let's say that let's say the parametric equation looks like this. The tangent at this point right here, which happens to be when t equals, this is when t equals 2. And I can't draw this line down because this is x, right? But the parameter which we're using, t equals 2, doesn't exist on this graph. This graph is plotted in respect to time. This is y and only x. So t doesn't exist on this graph. We just know that this point here is from t equals 2. So now this one, we know that the gradient is 5 over 2. Okay. And so if the usually I use the y equals mx plus c, and obviously it's an easy thing to do, right? You just find x at t equals 2 and y at t equals 2 and then solve for c. But I want to show you something that in class we did, and it blew my mind. I've never seen something like this. But let's say that there is a graph, and let's say this is just a zoomed in part of the graph, right? Let's say this is just the parametric equation of let me do this really quick. Parametric equation of ft and gt. This is just a function of that. When we have a gradient, right? The tangent line, the equation for it, I'm gonna write it down here. The tangent line, the equation for it is y minus y1 equals to m multiplied by x minus x1. What does this mean? It means that y, we just say, like, how we say y equals mx plus c, and the final equation could be like y equals 10x plus 15. You know how we leave y and x in? That's what the y and x's here are. Y we just leave as y, and x we just leave as x. But y1 is simply the y at this coordinate, so this would be x1, y1. So then we sub in the values of the x and y's at that point into this equation, and that's the full equation of the tangent line. And if you expand it and everything, that gives you the plus c, obviously, and you can do the y equals mx plus c. But in this case, we're going to take the shorthand method and try using this because I think it's a really good way to kind of use it as a short way. So let's find x. Let's find x at t equals 2. And what is x? X is t squared, right? X is t squared. So therefore, at t equals 2, x is equal to 4. Y equals t cubed minus 2t. So then that's equal to 2 cubed is 8 minus 2 times 2 is 4, so that's going to be equal to 4, right? So now we have x1 and y1 is equal to 4 each. Both of them are equal to 4. So the x at t equals 2, when t equals 2, the x position of the particle is 4. And when time is equal to 2, the y position is 4. Therefore, the tangent line, the equation for it would be y minus the y position that it's at, which is 4, is equal to the gradient, which is 5 over 2, multiplied by x minus the x position, which it is at, which is minus 4. So there we go. The equation of the tangent line, we can say, is y minus 4 equals 5 over 2, x minus 4. And if you expand this, it will give you the traditional y equals mx plus c4. Okay. Let's move on to the second component of this question. It says find the points on the curve where tangent line is horizontal. So keep in mind that first of all, we're going to find t. Which values of t satisfy the conditions for the tangent line being horizontal, and then we need to find the x and y coordinate of it as well. So it's a multi-step process. So let's remind ourselves, when the tangent line is horizontal, what does that mean? That means dy over dx has to be flat, which means it's 0. It's not changing, right? And for a fraction to be 0, remember that dy over dx is equal to dy over dt over dx over dt. Remember, the dt's cancel. So for a fraction to be equal to 0, the numerator must be equal to 0. Therefore, dy over dt is equal to 0 when the tangent line is horizontal. So let's say horizontal Therefore, dy over dt must be equal to 0. So therefore, what is dy over dt? Let's come back. Dy over dt is 3t squared minus 2. So 3t squared minus 2 must be equal to 0. Okay, so now let's solve this. So t squared, 3t squared is equal to 2, and t squared is equal to 2 over 3, and t is going to be the positive and minus root of square root of 3, 2 over 3. There we go. So now that we have the t coordinates, which is equal to root 2 over 3, and also equal to negative root 2 over 3, now that we have both kind of t solutions, we need to find the xy coordinates. So let's take t equals minus root 2 over 3 first. So the x coordinate of that would be that square. So, would be equal to, so let's say t equals the positive root first. If x is equal to t squared, then x would simply be 2 over 3. Now, y is equal to t cubed minus 2t. T cubed minus 2t. Therefore, it will be equal to 2 over 3 multiplied by 3, to the power of 3 over 2 minus 2 times root, let's just keep it exponent form, 2 over 3 to the power of 1/2. I'm going to keep it like this, but in a test, you'd obviously want to solve for this. Actually, this is probably one of the more simplified ways you can do it. Yeah, but this is a good way. So now we know that the first coordinate, the first one where the tangent line is horizontal, is 2 over 3 and this one. So 2 over 3 to the power of 2 over 3, power of 3 over 2 minus 2 times 2 over 3 to the power of 1/2. So this is the coordinate. This is the x coordinate, this is the y coordinate, and it corresponds to a spot on the graph. And that spot happens during when time equals the root of 2 over 3. So it's a little bit complicated to kind of wrap your head around with the 3 variables, but this is it. When it asks you for the position, you need to give it in terms of x and y, like the x and y position. Okay, so now let's keep on moving to the second position, and now this is when t is equal to the negative root of 2 over 3. Okay, so therefore x is the square of this. X would still be at the same spot, right? Because the the minus sign turns to the positive, and the square of this is the same as before. So x equals 2 over 3, and y is equal to, we just sub this in, so the minus comes out because it's a cubed, 2 over 3 to the power of 3 over 2 minus root of that, I'm not sure, minus root. You can't have a root of a negative number, can you? No, that's why we're not doing it. It's not a root of a negative number. It's 2, sorry guys, we bring the minus, then we do 2, and then we just put this in, so it's just 2 over 3, the root of that, and because it's minus, we can take the minus of this, so the minus comes out, and it turns this positive. So yeah, sorry for confusing you guys, but again, we just give this the position here, 2 over 3, and this is going to be minus 2 over 3, 3 over 2, plus 2 over 3, 1/2. There we go. So yeah, again, this is the x, this is the y coordinate. So we do the same thing again for, let's move on to part 3. For part 3, we do the same thing vertical. Remember, if you want something, if it's vertical, it's an infinite gradient, and infinite gradients when we're dividing by 0, so therefore dx over dt must be equal to 0. Dx over dt is dx over dt is 2t. So 2t is equal to 0, therefore t is equal to 0. And now let's just find the coordinate when t equals to 0. So x is equal to t squared, therefore x is going to be equal to 0. Y is equal to t cubed minus 2t. I'm going to check really quick. T cubed minus 2t, yep, you put 0 into there. 0 cubed is 0, minus 2, 0 is 0. So y equals 0, and therefore the position where the graph is going perfectly vertical is 0, 0. And this is an x and y coordinate. So yeah, thank you guys so much for watching this video. It's just an introduction, it's a little bit more lecture style. It literally is my lecture notes, but that was an hour and 15 lecture, and we just did it in 24 minutes, which is really good. So thank you guys so much for watching. Have a good rest of your